Now we're going to go over question number 4. I will give you a moment to sort of read the problem and the language note at the top. And we see question 4 is basically asking us to select all the correct implementations of this clear last method to make it work according to its comment. And so the description says, return the result of setting the rightmost one bit of n to 0, if there are any. And so what this is saying is we're going to take whatever n the input is and find the bit that's the least significant or rightmost bit that is a 1 and set that 1 to 0. And we're only going to alter that particular bit. And so for this input, going from the right, looking for the least significant 1 bit, we see it's this one right here. And so that gets it to 0 in the result, right? That's what we return. If there are no 1 bits, for example, we pass in 0, then we want to return 0. And looking at one more extreme case, when all the bits are 1, because we're working with negative, right, where it's 1, 1, 1, 1, 1, 1, 1, we just want to set that rightmost or the least significant bit to 0. And so this is the resulting number, which happens to have a decimal value of -2. And so that's what this problem is doing. And I think the easiest way to approach this, since it's multiple choice, is just to go option by option and see, does this work? And so I think a good example to work with, at least at first, is going to be the 0B1101100. Let's look at this as sort of our example to test against. So option A says, first let's take 1 and flip it. And so we know the number 1 is 0B00000001, right? That's 1 in binary. We're going to flip it, and so we'll get something that looks like 11111110. There are more bits this way since we're looking at 32-bit ints, but whatever, we're just going to look at sort of these least significant 8 bits. So we flip it, and then we shift it left by 1, and so now we have 11111100 because we've moved the whole thing over to the left. And then we're going to return the result of ANDing these two numbers together. And so if we look at this mask alone, we see all it does is it just takes the right two most bits and sets them to be 0 no matter what. But that's not really what we wanted to do, right? Like, we just want to set one bit, the one rightmost bit, to be 0. And so this doesn't work in general. And we see for this particular example, it does not successfully set this bit or the least significant 1 bit to be 0, because ANDing these two together results in 1 and 1. And in general, we see ANDing these two together is not correct at all. So A is not our option. Okay, well, let's look at the next one. In the next one, we see we set some variable I to be 1, right? So that's this number. And then we're going to say, well, I is not equal to 0, and I and n equal 0, let's keep shifting I over and over and over. And so what does this do? Well, we're essentially saying, let's take 1, and if we AND these two numbers together, the only way it will be non-zero is if whichever bit the 1 is at happens to also be a 1, right? And so we're essentially saying we're going to compare just this 1 bit, and we're going to keep going and going and going and shifting until we find some number where shifting results in this 1 being lined up with another 1 bit. And so the 1 starts all the way at the right, and we keep going until we find a non-zero bit. In other words, we're finding the rightmost 1 bit. And so once we reach this point, we're going to fail out of the if statement, right? Because this is false, right? 1, or this number and this number ANDed together is no longer 0 because we found a 1 bit. And so at this point, we'll stop And then what would we do? Well, we're going to get the opposite of this, which is 1, 1, 1, 1, 1, 1, 1, 0, 1, 1, 1, because we flip it, and then we and this together. And so we see what we've created is basically a mask where everything is allowed in except for that one rightmost or least significant 1 bit. And so this works, at least for this example. And just to make sure, I'm curious what would happen if n equals 0 here. Well, then I is going to keep shifting, right? We have this like, the number is 0, 0, 0, 0, 0, and we have this 1 surrounded by zeros that we keep shifting and 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 shifting. And eventually we'll move off the edge until all we have in is zeros because we've kept shifting I too much. But at that point, I equals 0, which means we'll stop. And then we are going to return n and the opposite of I. And so if I is all zeros, that's 1, 1, 1, 1, 1, 1, 1, 1, 1. But 0 and 1, 1, 1, 1, 1 is just 0. And so we've returned 0 unchanged, just like the example said we should. So B works. Great. Then we have option C, which says subtract 1 and then and it with itself. And so this requires a little bit of knowledge of how binary subtraction works, right? But the core idea, let's think about subtraction in decimal, right? If we have like, let's say 23 and I subtract 5, right? I don't have enough here. And so what I do is I borrow from my neighbor, right? And then after borrowing from my neighbor, this becomes 13. And now I have enough to do the subtraction here because I've sort of shifted that over. And then I get 18. That's how decimal subtraction works, in case you didn't know. And so binary subtraction is pretty similar. If I have this number and I try to subtract 1, which I'm doing here, I don't have enough in this place. And so what I'm going to do is I'm going to keep asking to borrow from my neighbor until I find someone that has a 1. And so what will happen here is that we will keep asking to borrow from our neighbors, and we'll get 0, 1, 1, 1. And then we'll do that subtraction. And so we get 0b, 1, 1, 0, 1, 0, 1, 1, 0, because we did all that borrowing, right? Or sorry. Yes. So I'm really not that good at math, but what you get from this is this interesting mask where we see that the borrowing only stops once we reach that rightmost 1 bit, right? We have to keep asking borrow from our neighbor until someone actually has something. And so we see the rightmost significant bit is set to 0, right, in the result. And then everything else from now, it doesn't really matter. But now this is n minus 1, and we're going to mask that with n. Remember, n was just 1, 1, 0, 1, 1, 0, 0, 0. And so when we and these together, the result is that the rightmost significant bit is set to 0 because that's who we borrowed from. And everything else from then on had been 0 in the original number, right? Because they were not the rightmost significant bit. Rightmost 1 bit. And so these are also all 0. And so the result is the correct number. And so this one works. Now what happens if we try to flip instead of doing and? Well, flip says, or XOR, sorry, not flip. XOR says 1 only if the 2 input numbers are different. And so here that would look like 0 and 0 are the same, so it's 0. These 2 bits are different, so that's a 1. And right away, we know we can stop because this bit is not correct in the resulting number. We know that the correct number would look like this. And so right away we see Oh, this one doesn't work. Now, what about E? So how can we break this down? This one's kind of a mouthful, right? First, we take 1 and we're going to flip it. And so that looks like originally 1, and then we flip it to get 1, 1, 1, 1, 1, 1, 0. Then we have these two. And so I'm going to add 1 to that first because I think that will be a little easier. And so I see what happens is that adding 1 to this number, right? Just like normal addition, what you get is a number that looks like this, or -1. And so this whole thing is really -1. So now what we have is n and n plus -1, or n and n minus 1. But that's the same as option C. And so the trick here really is recognizing, oh, we already did this, right? And that works. And so E is also a valid option. And that is all of this problem.